Hey guys, welcome to video 49. I thought today we could take a look at the transistors we've been dealing with in the previous videos and compare their transconductance and take a look at why some of them have higher gain than other ones. And what we've got on the first page here is 5 circuits taken from previous videos that are pretty representative of the small signal Class A amplifiers that we've been examining. If we start on the left here, we've got the MPF 102 JFET common source amplifier, and it worked out theoretically the gain of this amplifier should have been negative 2.4. Experimentally it came out to be negative 2.2. Pretty close, but overall very low. So the MPF 102 is not a very high gain device. Occasionally you get one that'll give you a gain of maybe 6 or 7, maybe a little higher, but not very often. Now if we come over to the next circuit over using the LND 150, that's a depletion mode MOSFET that we looked at. It's a relatively low gain device as well. Using zero biasing, this circuit came up with a theoretical gain of negative 3.5, experimentally negative 3.9. Again, pretty low gain. Now if we go on over to the 2N7000, that's an enhancement mode device, and this is the drain feedback biasing arrangement we looked at. I just picked it because it's simple and it gave us pretty decent gain. The theoretical gain was negative 33. Experimentally it came out to almost negative 20. Now the DN2535 is another depletion mode MOSFET, but much higher gain than the LND 150. It has a GMO of 103 millimos versus 2.3 millimos for the LND 150, so it's a much higher gain device. And when we set it up as a fully bypassed common source amplifier, the experimental gain came out to be almost negative 18, not too bad, very roughly equivalent to the 2N7000. And then finally we have the voltage gain champion, the bipolar transistor. Here is a 2N3904 common emitter. Theoretically the gain was negative 100 based on some rough assumptions. Experimentally it came out to be negative 70. Alright, now let's go on over to the next page here, and what I've done is plotted all of the transconductance curves for these devices based on the typical parameters that I used in the experiments in previous videos. So let's start with the MPF 102, and here are its transconductance equation. We're assuming an IDSS of 6 milliamps, VGS off negative 2.5 volts, VP positive 2.5, and GMO is about 4.8 millimos. And here's its curve, and I extended it a little bit into the first quadrant here because sometimes you can use the JFET over here for very small voltage excursions. You don't want to forward bias the PN junction, then it stops working, but you can apply a little bit of forward bias and operate over here. But in any case, remember the transconductance is the slope of this curve at the operating point, and you can see it's never really that steep. All right, now let's take a look at the LND 150. All right, that's this green curve. This is a depletion mode MOSFET. Relatively low transconductance. You can tell because its curve is pretty shallow. It's just pretty much similar to the MPF 102. All right, the next one we're going to look at here is the DN2535. Okay, that's this one right here, and you can see this is a much steeper curve than either of the previous two devices, so it's much higher transconductance, GMO 103 millimos. All right, the next one to look at, the 2N7000. Okay, this is an enhancement mode MOSFET. Its curve is over here, and you can see that it's a relatively high gain device at these current levels as well. And lastly, we've got the 2N3904 and its transconductance equation. Now, I gave the typical parameters here: a saturation current of 0.1 nanoamps, V sub T 26 millivolts, and eta, the emission coefficient, about 1.5 is pretty typical. And that's what I used to plot this curve. and it's pretty close to what you would get for the average 2N3904 transistor. Now, maybe I'm kind of weird, but I think it's really cool to look at all of these curves at the same time on the same plot. It really gives you a good sense of how they all compare to one another. And we're going to do this same thing with vacuum tube curves in the future as well, so that's something to look forward to. All right, but right now let's move on over to the next page. And what I've done here is set Q points for each of these devices at 5 milliamps. All right, and then over here I calculated the transconductance, that is the slope of the transconductance curve at each of these points for each device. The MPF 102 has a slope of 4.4 millimos at this Q point. The LND 150 is about the same, 4 millimos. The DN2535 is much steeper at 19 millimos, and the 2N7000 has a transconductance of 45 millimos at this current. And lastly, the 2N3904, 128 millimos, or I guess we could think of it as milliamps per volt, but millimos is the unit we'll use. But now you might be wondering, how did I get a transconductance for the bipolar transistor? And it's really pretty straightforward. Remember, when we were analyzing transistor amplifiers, we would determine the gain using little re, the dynamic emitter resistance, and that was V sub T over eta times ICQ. All right, now it just so happens that the reciprocal of little re is the transconductance, that is GM equals 1 over little re. And we could have analyzed the circuits using transistors all along with transconductance instead of little re. It's just that it's not normally done that way, but there's no reason why we couldn't do that as well. And here's the relationship. So what I did was determine the slope of this line at 5 milliamps, and it came out to be 128 millimos, and that's how you determine transconductance for a BJT. All right, now what we could do next is rewrite the voltage gain equation for the common emitter amplifier using transconductance. Hopefully you remember that the voltage gain for the fully bypassed common emitter is negative R prime C over little re. If we write it in terms of transconductance, we have AV equals negative GM times R prime C, and that's all there is to it. And you can see the similarity to the FET analysis using this approach. And maybe we should have done it that way all along for consistency, but it's tradition to use little re, so that's what I did. Now, as far as the next video goes, I've got a few ideas I'm kicking around. I might build a number of the single stage amplifiers that we've looked at and play some chords through them on the guitar, and we'll listen to them and see what they sound like when they distort. Not super scientific, but that might be an interesting video. We're definitely sometime going to take a look at the distortion characteristics from a mathematical standpoint and understand, hopefully, why these devices distort the way that they do. I've also noticed a lot of 555 timer videos popping up lately, but I haven't seen anybody actually derive the timing equations for that device, so I might do that next video just for a change of pace. I think it's kind of cool and interesting, and nobody seems to have done it, so why not? And also, I'm getting a new oscilloscope tomorrow, so I'm sure that'll provide me with a lot of entertainment, and maybe I'll do something related to that. And lastly, it occurred to me while I was making this video that down here in the corner, we've got a picture. I think that's Tesla. And yeah, today is Nikola Tesla's birthday. So another coincidence, just like we had Alexander Graham Bell's birthday a few videos back too. So there you go. That's all I've got today, and I will catch you guys next time around.